Is set known to everybody? Like, do you know set theory? Okay. So let me consider a set like the numbers 0, 1, 2, 3, 4 in this way. So this I am defining to be set of natural numbers. This was one of the first things what people discovered from like ancient times, like from Egypt, Greece, and also in India. We had a lot of contribution regarding this. So, what I will try to motivate you through, like how do we proceed from this set of natural numbers to the next case. So, yes, that's a good question. So, some notation here which will not include 0, but let me for this term let me include this. Yes, but you are correct. So, in real terms, I mean, in many definitions, you will see like it will be only starting from 1, not from 0. Okay, so then get solution is x equal to 2. And similarly, if you take like x plus 2 equal to 0, then this gives you x equal to minus 2, right? But now this number, this does not exist in this. So what I am trying to say is, so when I take the solutions of the linear equations, then I get something, it's denoted by z, is essentially known as like a set of integers. Right? So this you must have seen. I mean, like essentially it's like plus minus n. I mean, so you get all the natural numbers along with its negatives. So I am still with the linear equation, but you see here in this linear equation, I have 1 here. Like I don't have any coefficient in the first term. So let's take the next step. So let me now consider like solutions of some equations where I put some a in front and then I consider ax minus b equal to 0, and now I take ab in integer. So what do I mean by this? Now let's see. So if I let's say 2x minus 3 equal to 0, then this gives me x is 3 by 2. Right? We know what is it called? It's like a rational number, but now see this set is not in n, of course it's not also in z, so we define a new set which we call q. So it's like set of rational numbers. Yeah, perfect. So essentially what I am doing is I am somehow, so let's say this is like the lines. Sorry, it's a straight line, you have present. So here first I put 0, 1, 2, 3 like this. This is the natural line. Then I have put the minus, which makes me the integers. And now what I am trying to put is I am trying to fill up the gaps. So here for example I can put now half, here 1.5, and in this way it goes on. So those are the rational numbers. So essentially what I am trying to say is I have started from n. This is actually, so I have started with n. This is contained in integer. This is contained in q. And then I will see how I can continue. And my way forward is through this equation. Now see, if I have the linear equation, now can we imagine any sort of other combination which is not already existing? It is already there, right? The linear equations are already exhausted. So the natural next thing to consider is, like let's say I take x squared minus 2 equals. Right? So what can you say about x then? Plus minus. So now the next question is, like, is root 2 rational number? No. And you know why is it? So, yes. Okay. So I'll not go into the proof. Like you can of course then see that root 2 cannot be written as, like here, let me be a bit more precise. So then Q, this can be actually written as A by B, such that A, B is in Z and B from Z. So essentially what you are saying is root 2 cannot be written as A by B, such that A, B inside Q and B not, right? Yes. Okay. What's the next natural thing to do? We just include it in the set. Yeah. So the trouble is, how do we define some? Like here, see, here I had some very nice equations which was giving me the sets. But now what I want to do is, it's always not possible to form a set which is like a solution set. So then what we do is, so let me now write down this root 2 approximated by rational numbers. Okay. So what I want to now do is, I define a new set, real line, which I guess again you know. So this will be kind of set of approximation of the rational numbers. I will not be any more precise than this. And then since here now I can write like R. Yeah? So now what I am trying to do is root 2, you actually know that if you take root 2, somehow you can get in between somewhere here. You get a number root 2 here. Yeah. So essentially what I am trying to do is, this approximation technique is kind of trying to fill up this line so that I don't have any gap in the line. So what do I mean by now, like how much more I can do, or like let's say, I don't know if you know this term, it's called continuum. So like how many numbers are left now in the line? I mean, can we still find some numbers which are not existing here? So my other question is, can I continue this story?
Yes, sir.
Yes. How?
Sir, by dividing by imaginary numbers.
Yes, perfect. So as he has said, let me continue with the equation. So see, I have already considered x squared minus 2 equal to 0. So a natural question is, what will happen if I consider x squared plus 1 is 0? So I mean, then immediately you can see, since this means x squared is minus 1. So now x, people can, I mean, when you do the solutions, then this solution does not exist in real line anymore, right? Yes. So essentially what you do, you put a new variable such that I squared is minus 1. So this means actually I power 4 is 1. And then, like it's the, as I was trying to motivate you, how do I create a new set which will have solutions like this? So then what I do, I create this set C such that set of all A plus BI, where I is this number, and such that A, B are coming from real numbers. And you know that this is actually called a set of complex numbers. Right? Yes. So then R, essentially I can continue C. Right? So now naturally again, since I am following up, the next question is, can I continue any further? Any guess? So if you follow up till now, what is the way I am trying to extend the sets? By finding out some equation whose solution does not exist here, right? So to extend this, what do I have to find? So I have to find some polynomial fx Like let's say some x cube plus some 2x plus 3, something like this. I don't know, maybe this will not work, but somehow I have to find some x1 such that fx1 is 0, like solutions of this equation, and then x1 must not be in complex number. Right? That's the only way as I have been motivated. Right? Unfortunately, this will not read. There is a very important theorem. It's called fundamental theorem of algebra. So this says that any polynomial in C, so that means like the coefficients are in C, this will have a root in the complex number. Okay?
Yes.
So what does that mean? So that means this process now has to be stopped. I can't find any more equation whose solution would actually extend the field. Okay? And that's why later, I mean much later, this field is called something called algebraically closed field. Okay, so what does that mean? That means that you can't extend anymore. So everything has to be inside C. Okay? So essentially this gives you, I mean if you follow my now these fields, this will actually really should remind you the syllabus of your NCERT syllabus also. I mean actually that's how you go like this. You actually start from natural numbers and then Z. I guess there you study fundamental theorem of arithmetic, which I am just going to come now. Then you study rational numbers. Then you study surds and indices. I guess that's another chapter.
Yes.
And finally, I guess in 11, 12 you study the complex number. And one should wonder like why we don't study anything else, because you can't. That's the limit. Okay? Hence the story how much we can go. So now let me come to So now let me come to this line in some sense. So you see the way I have framed this, in some sense, if I know this integer, or in some sense n, this is equivalent, somehow this helps me to form q, and if I know q, q helps me to form r, and if I know r helps me to form c. So it's essentially this brings me to the next point. So important to study integer. Okay? And as I was just now telling, here now, I guess everybody of you have studied, there is a very important theorem, a fundamental theorem of arithmetic. So do you know what this says? Sorry? Yeah, can you tell what does this say?
Every composite number can be represented in a form of its product, of prime numbers, and where the arrangement of prime is used.
Okay. Okay, written as product of some prime, where I take product of this prime. Is this okay? Is this notation fine? Yeah. So then let me ask another basic question. Does everybody know what is a prime number?
Yes.
Yes. Perfect. So see now what has happened by this theorem. What's the exact content of this theorem? So it says that every integer, or I mean it can be, you take even the minus of this and also it's fine. So every natural number, this can be written as a product of primes. So like in some sense, like I mean if let's say if it is 32, so then this is like 2 times 2 plus 5, is it? Yeah. Sorry? You can go like 15 would be like 3 times 5 in similar way, right? I mean, so essentially what now, let me come to the next point. So what this theorem tells you, if we want to study this z, like the integers, it's enough to study it as product of prime numbers. So if we know in principle the prime numbers, then that should give me the idea to how to study the integers. Right? Okay. So that's the next part. Like, what do I mean by prime numbers, or what do I mean by the study of prime numbers? So I hope I have been able to convince you like that it's very important to study prime numbers. Okay. So now, as you have already told the definition, so you know the definition. But now, let me ask you some, or let me explain some very basic properties. Somehow, like what happens, prime numbers are very mysterious. I mean, so let me somehow say, for example, so suppose I take 5, 7, and then suppose I take like 11, 13, and in this way I go around like 17, 19. So are these whole set of primes like?
Yes.
Yeah? And these are like 5 and 7, these are like consecutive primes.
Yes.
So I define this kind of primes as something called, in mathematics, it's called twin primes. Yeah?
Yes.
Okay. What do I mean by twin primes? So naturally the question should be asked that, I mean, do we have like infinitely many of these kind of pairs? Yeah? Like here I am just writing 3 sets. Can I write infinitely many? But then immediately you should ask me, like, I mean, I am not considering infinitely many pairs, but what about first infinitely many primes? That you should first ask, right? So the question is, do you know whether there are infinitely many primes? So, do you have any idea, like, or first of all, what do I mean by infinitely many primes? Not infinitely many primes. Okay, is there any other opinion?
There are increases. Like in the first 2 digits, it's more, but as we move forward, like 5 digits, it's very rare. But there exists.
There exists infinitely.
Yes.
Okay, the opinions match. So, as one opinion says, like there are finitely many primes, right? Okay, so let me take some set S, such that P1 to P2 to PR. So this is a finite set I can take for R sufficiently large, right?
Yes.
So this is, so now this is what I have taken. It's like set of all primes, right? According to the comments, I'll come to your comments. But now let me define an element like a number. I define is like capital P, and I take product of all the primes. This I can do. This is also integer, and then take plus 1. Okay? Yeah.
Yes.
So now first question: does Pi divides P? Is it true? Why? So like, let's say, if it's too complicated P1 to PR, let me say I consider R equal to 3. So that means I am now considering P is P1, P2, P3 plus 1, right? So what I am asking is whether P1, P2, P3 divides this. Exactly. And P does not divide 1, right? So then this number, this capital P, so this number you already have said that P1, P2, P3, they don't divide P. So what are the choices? Either it can be a prime,
Yes, sir.
but then I have contradicted my choice. I have chosen P1, P2, P3, so this is a new prime.
Yes.
Or you can say like this is not a new prime, it can be a composite number. It can have factors. But as you have just now said, if it has factors, these factors can it be P1, P2, P3? So that means what? You have found a new factor which is different than P1, P2, P3. So that just shows you, like, if you have any finite set, any time, that just allows you to construct some new number, which is a prime which is different than this prime. That's correct? Is it? So you understand now where does it go wrong? So even if you assume R to be made very big, but any time if you assume the finiteness of the set, then you can create some extra unit. And that exactly shows that there are infinite units. So this was actually proved by Euclid some long time ago. And now of course there are many different proofs of this infinite many primes you are mentioning. So let me make a remark. So the question is how frequently. So the question is how frequently this capital P is a prime. So what do I mean by capital P is like product of all. So let me continue here. A prime number, let's say P, I can define a number, let's say capital P, which is like product of all P plus 1 such that Pi is less than P. So it's exactly like this. So essentially what I'm saying is take any finite prime P and then you take product of all the finite primes up to that prime and then take plus 1, which was the set what we were considering. So the question is how frequently this is prime. Right? Because this was one of the arguments I used. You remember what did I say? That either this is a prime or this is composite. But the good point was even then I could find a factor which is a different prime than the existing. And as he said, this is really true. This is now proved that this P is hardly, if you go very far, then this is very rarely this is a prime number. And I think now there is a like now since we have very good computer, there is a calculation I think. Yeah, it says that if you take P is 42,209, then essentially like product of Pi less than 42,209 plus 1, this is the prime. So this was done I think in 2002 or something. So it took, at least according to the publication, this took almost 1 year of CPU time to compute that this is the prime. So this can be very difficult and this can be very time consuming. But yeah, anyway, but that's very rare as he also mentioned. So now once I am happy with that there are infinite many primes, let me check the time. How much time? It's up already. Sorry. Okay, I'll just finish with this. So then now you are happy that this is infinitely many primes exist. Then you come to the next question, whether infinitely many twin primes exist. And that's actually a very famous conjecture. This is called twin prime conjecture. So this is still largely unsolved, and some cases actually were recently solved. I mean, and then people actually got Fields Medal. I don't know whether you know Fields Medal. That's like the highest award one gets in mathematics in this year. Okay, so these are really like a very important problems what we are still trying to resolve. And I'll just finish in 1 minute, just saying some remark. These are like theoretically quite nice, but in reality, the prime numbers do really have a very important application in real life. So there is a string called like, so prime numbers have real world application towards a branch which is called cryptography. So I don't know whether you have heard this term or not. So this is like a kind of a security system. So in general, what happens, like everybody of us, I guess now we are using ATM and phone pay and everything, right? I mean, and you also use credit card, ATM card, everything. So every card has some security system. And those security systems really, has to be built on some security theoretical background. And there is a kind of way to use the prime number like factorization. And you relate this with the security system. So I don't have time to explain this in more detail, but essentially it boils down to, you see now, if I give you a large number, then it's very difficult to factorize into in prime numbers. And that difficulty is kind of proportional to the difficulty of the security system, how it's difficult to break. So essentially, what I am trying to say is, regarding these theorems, it might at some instance might look like this really doesn't matter. I mean, whatever is the world people are doing, I don't care, I just prove this twin prime conjecture. But these primes, they really do matter in some sense, where maybe this will be used in security systems. Okay, I'll stop.
Thank you for the talk. And are there any questions?
I don't know actually what is co-prime.
So two numbers.
Co-prime. No, it will not happen, right? Because prime numbers are only them as factors. So co-prime prime numbers cannot. Any other questions?
X is equals to plus minus 2.
No, we take x square minus 1. Yes.
Answer, you wrote the solution that x equals to plus minus 2.
Yes. Yes.
Sir, how can this be possible? Plus minus 2.
So that means x square minus 2 is essentially x minus
So
root 2.
it should be like x equals to root 2.
Yeah, so it's like this polynomial, you are factorizing as x minus root 2 times x plus 2. So both are roots of this polynomial.
Alright.
So that's what I mean by plus minus.
Alright. Answer, it may be a senseless question, but it's like why 10 comes after 9? And like 0 comes, these are defined, 0 to 9 numbers are defined, but why 10 comes after 9?
So let's say, I mean, if you want to answer this, so then I have to ask you, what do you mean by 9?
So 9, so actually I don't know.
Yeah, so it's in some sense like, yeah, like we have a decimal system, that's where we are trying to do it. Like that's in the decimal system, then we are doing everything in base 10, then 11, 12, right? But in, like, I don't know if you have studied in computer science, you will have know like knowledge of binary system, right? So what's the binary system? So binary system essentially, so it's like 0 and 1, right? Yeah, so it's the magnitude of 2. Here I'm taking, it's kind of like in base 10. Here that I will say base 2. Okay. So in that way you can actually not only binary, you can form like 0, 1, 2, mod 3 essentially. I mean like here you write every number, you can write in terms of 0 and 1. In similar way, you can write any number in 0, 1, 2 also. It goes on. So in that way, like in 0, 1, 2, 9, 10, this is another system.
After exhausting first digit, one digit number, second digit is this is the existing. It could be a prime number if it exists in a hypothetical existence.
That's again, I have to ask what you mean by biggest number.
So I mean the end, like in the temperatures we have end like 0 Kelvin, below that is not possible.
Yes.
Something like that. So could it be a prime number if it exists?
Yeah, if it exists, then it means it's a finite number, right?
Then you can add plus 1.
Then you can add only plus 1, then it's even. So it's, I mean, that's the trouble with this concept of infinity, right? I mean, you can never somehow pinpoint. Once you say that this is a number, then as Sir said, you can add one number and then that's a bigger number than what you get. You can never kind of get a hold of this.
First of all, very good. The unique prime because it is the only even prime number,
Yeah.
and I don't think any other prime number that is even. So, sir, if there are any other quality of prime numbers that any other species has that who is a unique prime number, it is even. So, it is like any code.
I mean, in that sense, you can say 3 is the minimum spot prime number. I mean, but yeah, you are correct. 2 is always a troublesome. I mean, in future also, like even in our research, we always try to avoid 2. I mean, because 2 has this unique property, right, as being given. So, in general, like it makes a lot of trouble for proofs and computation. But yeah, otherwise, I mean, if you are asking like there are some unique properties to characterize some primes,
Yes.
of course there will be many separate things. But unique as 2